Welcome to the first Friday seminar of the semester. Today we're very happy to have Beatrix tell us about the complex Liouville string.
Very good. Thank you so much, Sophie. Yes, so today I'll be telling you about the complex Liouville string, which is based on work in progress with truly outstanding collaborators, Scott Collier, Lorenz Eberhardt, and Victor Rodriguez. But I have a tendency to run around here. So, but before I'll tell you in more detail what the complex Liouville string is, let me just zoom out for a second and tell you about a persistent paradigm in the context of low-D string theory. And the persistent paradigm is that some 2D string theories, which from a Worldsheet perspective, you can view as a meta CFT coupled to what's called the Liouville CFT in such a way that the total central charge is 26. So this 2D string theory that makes a dual description in terms of amplitude central. So that's the bigger picture here. And if you're now going back a few years, like late 80s and early 90s, then this bunch of gentlemen over here, what they studied is that they took for the matter CFT and minimal model. A minimal model is a two-dimensional rational CFT. It's labeled by two co-prime integers. Do I have a pointer here as well? Oh yeah, wonderful. So for the matter CFT, basically, they took a minimal model, which was labeled by these two co-prime integers. And so, for example, like the IC model is a 3-4 minimal model. So let's say you take one of those minimal models, so labeled by these co-prime integers P and Q, and you couple it to this Liouville CFT in such a way the total central charge is 26. And then it turned out that there's a dual description of this Worldsheet theory in terms of a matrix. In this case, when P and Q are just co-prime, and none of them is 2, then it turns out to be a 2 matrix interval that's dual to this Worldsheet theory. If you specify one of those integers to be 2, so and since they still need to be co-prime, P needs to be odd here. So for example, the Yang-Lee model is a true 5 minimum model. So you couple this 2P minimum model to Liouville, always in such a way that total central charge of those two theories is 26 to make it a critical string theory. Again, you get a 1 matrix interval in this case. So if you look at these two examples, in case one of those P or Q here is 2, then in these 2 matrix intervals, to go down to 1 matrix integral, it means that like here, if one of those is 2, then you can just integrate out one of those matrices. In this 2 matrix integral, it goes back to the 1 matrix integral. So a few years back, in a very nice paper, Sarchecker and Stanford embedded ADS2 JT gravity into this paradigm. So that's when maybe you have encountered this matrix integral string theory duality. And later on, it has been observed that there is actually a stringy realization of ADS2 JT gravity as a semiclassical limit of this 2P minimal string. Here, semiclassical means that I take P to infinity. In other words, I take the central charge of this minimal model to be large and very negative. And later on in a paper of last year, with the same collaborators, Scott, Lorenz, and Victor, we showed that also a so-called Versor minimal string gives you a stringy realization of ADS2 JT gravity. So now, why dwell on this low-D string theories? So I think the interesting thing here is that in these low-D string theories, they're very controlled. They're very tractable. We can do a lot of explicit calculations. But at the same time, like these low-D setups, very often they contain a lot of features of higher dimensional holographic dualities. But in 2D, we can really prove this duality. So some of these dualities, like we can explicitly prove, we can really calculate all the things. But non-perturbative effects and so on and so forth, they're present here as well. But in 2D, in low-D setups, we can really calculate things, which is most of the time out of reach in higher dimensions. And another question that's been of interest here is like, can we also say something about the sitter? So I think it's okay to say that the sitter in low dimensions has been studied, but a unifying theory, a common accepted theory of sitter quantum gravity is still out of the picture. So, but going back to this drawing that I had before, and maybe I should have stressed. So what I plotted here is the matter central charge. So this is the complex plane labeled by the matter central charge. So I discussed these two setups before, these two minimal string theories here. the Berzor minimal string is this orange setup over here. I won't unfortunately have time to discuss this in detail, but since I'm here, so if you're interested in the Berzor minimal string, just come find me in my office. But the theory that I really want to talk about today is the complex level string, which in this picture is this green line over here. And the complex level string is made out of like a meta CFT, which in this case is no longer a minimal model, but it is itself a Liouville CFT. It is itself a Liouville CFT with complex central charge. So it has a central charge whose real part is 13, and then we give it an imaginary part. And we couple it to its complex conjugate sibling in such a way that the total central charge of the two theories again adds up to 26, because the imaginary part is killed if we add this complex conjugate theories up. And as we will see, it has a dual description in terms of the two matrices. So again, zooming out, I mean, this is a very cool picture, I think. But of course, the question remains, can we completely classify this landscape of 2D string theory matrix integral dualities? Very good. So this is the bigger picture motivation, but I think it's time to go through the complex level string, unless there are any questions.
By the diagram. Should I interpret it very literally or just?
It's a comic.
Okay.
It's a comic. It's just to give like a gist of what's going on. Like, so I mean, the secret one string is not there. Some things are not there. Like it's a comic.
Okay.
Right. So the complex level string. It has roughly, at least I think what we studied so far are 4 different aspects, or actually 5 different aspects. So I think maybe I'm going to be too ambitious if I want to tell you about all these aspects. So let us see how it goes. If I skip something, like I'm happy to discuss anything later on again. But so one of the aspects that I want to tell you about is the Worldsheet description. I want to tell you about the main observables in this theory, which are the string amplitudes. I will then tell you that there is indeed a 2-matrix integral description of the complex level string. I want to tell you that there is a relation between the complex level string and both DS2 and DS3. And I think there is interest in the audience to also discuss some non-perturbative effects. But let's see how it goes. So let's start with the Worldsheet description. Right. So the Worldsheet description of the complex level string is this green line basically. So it was a Liouville CFT with central charge 13 plus I lambda. So if you don't, normally I put a superscript. If you don't see a superscript on the central charge, for example, it's always a C plus theory. So it has the central charge 13 plus I lambda, so lambda is real here. And we couple it to its complex conjugate 13 minus I lambda. So I won't unfortunately have time to explain to you in detail what Liouville CFT is. So the one punchline to take away from Liouville theory is that Liouville theory is a 2-dimensional non-compact CFT, meaning that it has a continuous spectrum and a non-normalizable vacuum. As a 2-dimensional CFT, Liouville theory has a central charge. And it's commonly used to parameterize the central charge using this parameter B. So often like this combination B plus B inverse is also called Q. So, and the vertex operators of Liouville theory, they're all scalars, which means that H is equal to H tilde. And then people, it's again like common to use the parameters, this following parameterization for the conformal dimension as C minus 1 over 24 minus P squared. So P is called the momenta, P is continuous. And to have really like a well-defined Worldsheet theory, of course, the conformal anomaly has to vanish. So all the central charges have to add up to 0. Or like C plus C minus has to be 26 and then killed by the ghost. In terms of the B parameter here, this tells you that the B minus, which is the B of the second theory, is talking to the first B in this way. And for the central charge, so for this B parameter to really make this central charge, this parameterization to be of the form 13 plus I lambda, that B gets a face. So B is now along this 45-degree line in the complex plane. Yes.
How do you know which 45-degree line P?
It's a choice. We made a choice. So it could be plus minus. It could be plus minus here. We made a
Now
choice.
for B, there's a choice, but does that determine the choice for P? Once you've chosen which line B is on, you put P in the opposite line from B.
It was a convenient choice to make. You mean this P, right? You mean B and P?
You made a choice for B,
Yes,
but is there an independent choice for P, or is there a reason P is on the opposite line from B?
it was a choice. It was also a choice. Yeah, so taking ahead over the P, so to have a well-defined string theory, we needed the conformal dimension to satisfy the Marshall condition, so H plus H minus needs to add up to 1. And it was convenient for us to also assume that the conformal dimensions are complex conjugates of each other. And this two constraint, like Marshall plus this complex conjugate, put P on a 45-degree line as well. It was convenient for us to choose them on opposite lines, so that V times P is real. But it was a choice.
And the opposite choice would give an equivalent theory?
Yes. Actually, we will even see that like this, like there's some invariance that we go to 1 over V and which will just put it on the other side.
I see.
Of course. Very good. Any questions on this? This is an important slide. So actually what I should stress here, so maybe this 45-degree line, if it's hard to remember, but what this also means, so if B is along this 45-degree line, if P gets this face, then that means that P squared is pure imaginary. And then in particular, this means that this conformal dimension is of the form half plus IR. So if this rings a bell, great. If it doesn't, like we will get back to this like at some time later. Right, so this is the complex level string as a Worldsheet theory. So what is incredibly remarkable about Liouville theory, and which is the reason why like there's lots of studies of Liouville theory, is that this gentleman over here, Dilaton, the Somologicals, and David Teschner, they have solved Liouville theory. In the sense that they have found the structure constant of Liouville theory. So if you take this vertex operators and calculate the 3-point function, then you get this CB over here, which is known as the DOZ formula, as the structure constant of Liouville theory. And I think I put this equation over here. You don't need to memorize this. It's just that for people who have never seen this, to be like, okay, the expression is really explicit. So this gamma B is a function that has an integral representation, but we know its poles, we know its zeros, we have a lot of control of this gamma B. So this is actually a neat looking formula. And very good, but once we know the structure constant, all the higher point correlation functions, they can be obtained using some common form of block expansion. So basically, Liouville theory as a CFT, as a two-dimensional CFT, is solved. And so then we can put all these ingredients to good use and look at the unshelled vertex operators of the Liouville squared string, of the complex Liouville string. And as I told you before, so this is the VP plus, is the vertex operator of the first theory, like the 13 plus I lambda theory. And this is the vertex operator of the second Liouville theory. And it's IP here because this was the Marshall condition. And then we study these things over here, which are the string amplitudes of this complex Liouville string. You can really ignore these prefactors here. In the literature, like they often call leg pole factors, it's some normalization of the vertex operators that we put there to make everything look pretty. But the important thing is this ingredient over here, so the correlation function of Liouville theory, the ghost, so CC tilde over the ghost, and this is the integral over moduli space. Now, what's interesting in this expression is that it's an absolute value squared. And this really comes because we looked at the complex conjugate Liouville theories, and we imposed the constraint that the conformal dimension of the two Liouville theories are complex conjugates of each other. So that's the reason why I have an absolute value squared here. And what's remarkable as well is that this moduli space integral is actually absolutely convergent. So we can put this, for example, on the computer, and like not for a super high GSM, but we can put it on the computer, and there is nothing like this integral absolutely converges. So now in general, of course, this is still hard, but let me give you an easy example. So the easiest example is this 3-point amplitude. So I put 3 holes in this 3-punctured sphere. So the 3-punctured sphere, like there's no moduli space integral to be done. It just takes the structure constant of the first Liouville theory, this 13 plus I lambda Liouville theory, and the structure constant of the second one. And again, this B and the minus IB is, and the P and the IP are such that we have variation conformal anomaly and the Marshall condition. And then, fortunately, Somologicals has actually already looked at this for us. And Somologicals has uncovered that by just studying like the pole structure and the zeros of this DSZ formulas, you can write down this string amplitude in this neat looking way as in terms of like theta, Jacobi theta functions. And if you massage these Jacobi theta functions, there is actually this pretty cool looking formula here in terms of an infinite sum. So m here is an integer, and it ranges from like all the positive integers. So we will see especially like this formula popping up later again. Any questions? Okay. So, but still, like in principle, so this was a three-point amplitude, where there was no moduli space integral. If you go for anything beyond this, it's hard. And so, and this moduli space integral, to really evaluate this, like you can put it on the computer if you want to for some low g and n, but afterwards it becomes very difficult. So the idea that we tried to push here is that, so in this regime where the B and the P are on both at this face, AGN, like the string amplitude, is absolutely convergent. Now let's get the momenta away from this, analytically continue them away from this 45-degree line. And then exploit all the things that we know about Liouville theory, all the things that the semologicals and many other people have told us about Liouville theory already. So we can then really, like, once we analytically continue the momenta away, we can harness the analytic structure of the AGN to develop some sort of bootstrap technique. So it's not the conventional bootstrap, it's just some bootstraps over, like, you look at you impose all the constraints that we have to bootstrap this string amplitudes. And a lot of those constraints come from the Liouville CFT correlation functions. So these Liouville correlation functions, they have discontinuities, they have poles. And so we basically just imposed all these constraints that we had, that we knew this string amplitude has to satisfy. And additionally, just by staring at the definition of the string amplitude, you infer it has some kind of duality. So if you send B to minus B and B to B inverse, it has to behave like this. And if you use this thing that we call swap symmetry, it's because under this symmetry, the two Liouville theories get exchanged. So that's why we call it swapping. And then the string amplitude has to behave like this. So basically, by just really imposing all these constraints, you can, and for A0, for the four-punctured sphere, there's also this method that's called equations of motion. It's very beautiful, but I will not have time to discuss it right now. But basically imposing all these constraints, you get this. So you don't need to memorize this formula because you will see like rules to derive this formula, like some sort of Feynman rules later on again. But the thing that I want to take, the takeaway message here should be that there's a way to get this Worldsheet integral without having to do any explicit integral. And you get this remarkable looking formula. So, and but an important ingredient here is also to see this V0 form popping up here. So very interestingly enough, these are the string amplitudes of the Versormen string. So this just, like, we did not know why this happens from a Worldsheet perspective, but this is what popped up.
So those conditions can completely fix this function? Okay.
Yes. I mean, we did it for A04, for A11, and then we stopped because we found the Medis integral, which was doing us an easier, which was helping us a lot, but in principle, you can. And
Sorry, is that infinite sum convergent for n in complex B?
it is convergent because B squared here, I should have stressed it, so B squared is pure imaginary, B squared is in the upper half plane, and so this thing is convergent. And so these are they're pretty cool plots, I think. So just by using this formula that we bootstrapped, and for A04, you can put this AGN, like this moduli space integral on the computer. And so in putting it on the computer, you get this line here. And just plugging in like this formula from the previous slide, you get this pretty cool looking plots. And the error here is very tiny.
The formula you put in the computer is a formula that involves an operator product expansion.
Yes, exactly. Well, it's this formula with the conformal blocks in the sphere. It's really like literally this formula.
And the intermediate things you sum over. You need to
You just
sum over some intermediate states.
yeah, you need to integrate over the intermediate states in the conformal block expansion. Yes.
You need truncation of this? Like this m in the computer, do you need to truncate the m?
Oh yeah. Like sorry. Oh sorry. Yes. You mean the dot? Okay. So you don't need the integral. You mean like this thing here? Yes. You need to truncate them. That's all. Yeah. To create the dots, you needed to truncate the sum. But then you get like this plot here. So what I plotted here is A04 for, I don't know if you can see this, it's very clear. So this is where B is really along this, and has this 45-degree, has this P04 phase, and all the momenta are along the, have as well a 45-degree phase. So in this case, indeed, like the integral was an absolute value squared, which is why you see like one line here. Take whatever other like B and P, and then you can also basically evaluate this Worldsheet integral. In this case, the Worldsheet, the moduli space integral at some point is going to stop to converge. But for sufficiently small momenta, you can still control it. And so basically, this is sufficiently small momenta where you can control it. But in this case, it's not an absolute value squared anymore. That's why we have a real part and an imaginary part. So this is pretty cool. But
the numbers, the momentum you're choosing, why is this number? Because this number are very.
the log pretty. My collaborator is really like E over pi. I don't know, like it's E over pi here. It's just okay. It's numbers. I mean, the importance is that in this plot, the phase is always pi over 4, whereas in this case, the phases are just whatever. So and this 3 pi over 13, like it will make some kind of strange central charge. So it's just different, just something else. But I think we have multiple plots with different central charges, right? So in principle, if we would have not found
You just mentioned
Yeah.
if the P is large, the modular integral is a divergent.
So no. Here it will always be convergent.
Uh-huh.
In the case where the phase is pi over 4, the moduli space integral is always convergent.
Okay.
In this case, if the phase is not pi over 4, at some point your moduli space integral will cease to converge.
Do you have an explanation why that is happening? Because there are some poles
There are poles.
or some.
I have a picture in the end that I can show you, but then I would have to go for all my slides. So let me get to use in the end, so I don't. But I can show you. So it's really beautiful. It's very pretty. So in this case, there's really like there's really like a region that's like where it's always convergent. So in here it's always converging. So this is this pi over 4 base, and then the other case at some point it makes like some star, and it's like it ceases to converge outside here. So, and that's because of poles.
Okay.
Very good. So this was the Worldsheet, the like really brute force using.
Sorry, one more question. So beyond the poles is a formula you just bootstrap the still convergent.
Second.
So say there are some point like beyond some pole, you may have the integral to be not convergent, right?
You mean here?
Yeah.
Yeah.
But how about the formula before? That's one slide before. The infinite sum formula. Is this formula also divergent beyond those
You
points?
can analytically continue it, but I mean it ceases to converge at some point, yeah.
Okay.
Very good. So in principle, you can continue this bootstrapping techniques, but what we found is that actually the complex global string can also be represented as a matrix integral, and it is a 2 matrix integral. So a 2 matrix integral, the 2 matrix integral under consideration is this following object. So M1 and M2 are Hermitian matrices that are minimally coupled here, M1 and M2. V1 and V2 are potentials. And the observables in a matrix integral, at least before you double scale, so a double scaling means that I take the size of the matrix to infinity, and I'm going to zoom in into a specific region of the eigenvalue distribution. But for now, let's not double scale. So then the natural observables are the so-called resolvents. So it's this trace of x minus m1. And what we can also study is like products of resolvents, which is this object over here. And if you take the connected part, then they actually they satisfy some expansion of this form. So now let's look at the resolvent. So the resolvent has this x minus m1 over here. So if n is finite, the resolvent is going to have poles. Whenever x is going to hit one of the eigenvalues of n. If I take n to infinity, then these poles are going to smear out and they're going to give me some branch cuts. And these branch cuts are exactly located at the support of the eigenvalues. So that means that the resolvent, like in particular these objects over here, they're generally going to be multi-valued functions in the complex plane. And that's why we introduce the spectral curve, because the spectral curve is a Riemann surface on which the resolvent is single valued. And it turns out that the spectral curve for the complex Liouville string is this cosine expression. So the spectral curve for the complex Liouville string takes this form over here. I don't know if it's helpful or not, but for those of you that have maybe seen some the Sine-Schenker-Stanford matrix integral. So they're like x of z, that's squared, and y of z. What's the same? So these are just different. So it's a quantity. It curves out. It defines a Riemann surface on which the resolvent is single valued. Now, in our case, and for the complex Liouville string, the spectral curve is actually quite involved. In particular, it has infinitely many branch points. So the branch points you find if you calculate the differential of this x. So I'm focusing on one of the aspects, the parameterizations. There is a symmetry between x and y, so in principle I could do everything for y as well.
Are X and Y the two resolvents of the two matrices?
Yes, the discontinuity of x is going to give you the density of states of one matrix, and the discontinuity of y is going to give you the density of states of the other matrix.
Are the potentials for the matrices the same or different?
We don't know the potentials because we only know the double scale like.
But they're different because the curves are different.
So yeah. But I don't know if you still remember, I should have stressed this before, but so you see this little integer m popping up here in the branch points. I had drawn like the string amplitude for, it's a bit sad that I don't have that. But there was the string amplitude for like this A03 that was labeled by an integer m that was running over all the positive integers. So that's this m. So we are uncovering basically this m, the structure from the Worldsheet now in the matrix level. So I have this plot again, so you see this again. But so this is the spectral curve is infinitely many branch points. It has also infinitely many nodal singularities. So nodal singularities are points where the spectral curve self-intersects. So at this, all this expressions for z over here, the spectral curve is going to self-intersect. Nodal singularities are very important when we study non-perturbative effects. But we'll get to that later. But I don't know, for the experts in the room, maybe the spectral curve of the PQ minimal string actually looks remarkably similar to this. So you just instead of the B here, the B inverse, you have P and Q. So, but it's remarkably similar, which caught us by surprise, actually. So, and we don't have, I don't have an explanation for that. So I just wanted to stress this. Very good. But then, as asked before, so I'm always just going to focus on one matrix from now onwards. You can do exactly the same calculation for the second matrix. But studying the discontinuity of the spectral curve, you get the eigenvalue distributions. And so, for example, for the first matrix, you get this eigenvalue distribution. Let me stress here that so b squared was purely imaginary, so minus ib squared is real. So that's why like the argument here is really real valid, and the argument here is real valid. But nevertheless, so in principle, so if you plot this here, you would think that the support is on 2 to infinity. However, at some value E naught over here, which exactly corresponds to the nodal singularities of the spectral curve, which also means that it corresponds to non-perturbative effects, the spectral curve, the eigenvalue distribution becomes negative. Now, long story short, this point E naught is the point where we need to start taking into consideration non-perturbative effects. And so what we believe at this stage is that at this stage, the eigenvalue distribution will be lifted and we will nothing is going to be negative, which is of course totally unphysical. But for a perturbative expansion, all that we need is this region very close to 2, where we get the expected square root behavior and all is good. And again, like just stressing, like if you do the same analysis, you can also find the eigenvalue distribution for M2. It has the same structure, just that it's going to be supported on minus infinity to minus 2. Yes.
So the place where this thing goes negative is parameterized by b squared.
The E naught?
Yeah, the E naught.
Yeah, the E naught is cosine of pi b inverse squared.
Right. So is it clear that b squared can sort of be a parameter that tells you when non-perturbative effects become You would have expected maybe that there's some other parameter that's like a loop counting parameter. That will determine the non-perturbative.
That's an interesting question that I don't think there was any expectation there. So it just came out of the calculation.
So for small b, what is E naught?
So E naught is the cosine of pi b minus, I don't know, can you people see? It's the cosine of pi b inverse squared. It's the first nodal singularity.
So
So b squared is imaginary, so that's exponentially big if b is small.
Yes, I chose a specific choice of b here such that we can still see the zero on in my plot.
still a sort of a worldsheet effect.
I mean, you can also see it from a matrix integral, like in principle, like the non-perturbative effects you can also see from the matrix integral when one Eigenvalue runs away. But in all that I'm going to talk for like the next few slides, we will just need to take the perturbative expansion, and then this is really far away for us, so we don't care about this negativity for now. It's an important feature, of course, but it's for perturbative expansion, it's not going to like do anything.
How do you guess how to get the spectrum curve? Did you expand?
The spectral curve?
Yeah. Oh, okay.
Yes.
Yeah.
Function, not to
What do you want to match?
I mean, we knew, I mean, we had calculated A04 and A11, and like, so we had calculated some of string amplitudes already. And we knew the structure of the string amplitudes. We knew that it had like range cuts. We knew like how that it was looking like. I mean, you saw A04, right, before. So we knew roughly like how the structure was supposed to be, and then it was a bunch of guesswork.
Oh, okay.
I have brilliant collaborators as well. So, right, and
But in other words, you so you just match the first few others.
yes,
Okay, but you
Exactly.
haven't even checked even the recursive formula match on both sides.
let's get there.
Oh, okay.
So, but yes, I mean, I think when we started this project, it was unclear to us that there even is a matrix integral. So we were not expecting a matrix integral. So we found it, but it was not that we started with like, oh yeah, there has to be a matrix. So
It's maybe the same question that Herman was asking. Already in Liouville theory, you have this parameter which is mu, some coefficient, and that ends up being the loop counting parameter. It sounds here that you don't have that parameter, or maybe you do have it.
I mean,
It was a parameter you already were seeing the sphere, right? That was
Yeah.
the string loop counting.
I mean, I have a few slides afterwards where like I'll explain to you how you can get the string amplitude from a path integer perspective, but I still don't I don't think I know how mu would affect the calculation we've done so far. But yeah, so once you have the spectral curve, you can solve the matrix integral. Because due to this gentleman here, Einard and our team, who told us that there's a topological recursion for the spectral curve. Sorry, for the resolvents. This is like the loop equations in matrix. So you do give it this input data, so omega 0,1, you define through the spectral curve in this way. Omega 0,2 for every Hermitian matrix integral is always this form, it's known as the Bergman kernel. And then the resolvent and the omegas are basically related in this following way. So you add a bunch of differentials. And then this omega GNs, they satisfy topological recursion. And because the spectral curve has infinitely many branch points, it's a topological recursion with infinitely many branch points. Going back in JT gravity, like in the Sartre-Stanford, it was a topological recursion with a single branch point, like at z equal to 0. So here we're doing the same, but now with infinitely many branch points. And by empirically, we found this relation between the omega GNs and the AGNs. So, and then this gives you this pretty cool working formula. So now, like basically exporting like this topological recursion for the matrix integral and relating omega the resolvents basically to AGN, we found this formula here. And what this is basically a Feynman integral, Feynman rules expansion for the matrix integral string amplitude. So Feynman rules for the string amplitudes. So let me disentangle this for a while. So what we're summing over here are so-called stable graphs. So stable graphs, they enumerate the generations of a Riemann surface. So this is a trivial degeneration, there's nothing. In this case, the Riemann surface degenerates. So it degenerates at this nodal point over here. And then the infinity over here means that it is a stable graph, like it is infinitely many branch points. So it includes a sum over all positive integers, and these m's are again the branch points. But they label the branch points. So I give this Riemann surface a number m1, and this one m1, and this one m2, and then I need to sum over all these integers m's. All these integers. And so basically this is an expansion in terms of like colored Riemann surface, because this has a color m1, it has a color like m1, and this is a color m2. And once I hit an internal line, like a nodal singularity over here, I need to integrate over it. And then each of the vertices, so this vertex over here, this vertex, and this vertex is getting the Virasoro quantum string, so the string amplitudes of the Virasoro minimal string as a string vertex. But let's look at this in an example. So this is again this four-point amplitude from before. So A04, it has two generations, the trivial one, which is this one over here, and I need to sum over all the positive integers. And the second degeneration is this one over here. And they have two integers, m1 and m2. So m1 and m2, and like these integers are again like the branch points of the spectral curve in this interpretation. And then my formula told me each leg gets this sine, and here as well, sine, with m1 and m1 and m2 and m2. Note that b times p was real. For the internal vertex, I also get the sine, but I need to integrate over it. And each vertex over here gets this contribution, which is proportional to the quantum volume of the Virasoro minimal string. In this case, I just like gave you these two expressions. So V04 was this polynomial, and V03 is just one, because here this is a three-punctured sphere basically, and so it's V03. Whereas here it's a four-punctured sphere, so it gets V04. These are rules. So if you're in a train and you have a lot of time, you just like write down all the stable graphs for like, I don't know, G is equal to 5 and N is equal to 2, and then it gets incredibly hard, but you can do it. And then you just apply these rules. And then this is the final result. So if you bootstrap that thing, like if you bootstrap A52, you're gonna like, I don't know, you need to have a lot of time. It needs to be a long train ride. But from a matrix integral perspective, like using these Feynman rules, this is pretty straightforward. Very good. So these are the Feynman rules for the string amplitudes.
Sorry, here you mean you mentioned the volume for the Virasoro minimum string, which means you basically change the B and the B.
Yeah, so you analytically continued
Oh,
A, B, and B. Sorry, it's analytically continued for the volumes, yes. But from this perspective, it came as a surprise that we found them. So we just so they just appeared. So in principle, although I don't have time to explain this today, there's also a Mirzakhani type recursion relation for the quantum volumes. Please ask me later, we can discuss it, because I think it's actually pretty cool as well. It looks very similar to the Virasoro minimal string, but I had to decide whether Feynman rules for Mirzakhani recursion relation, and I decided on this picture.
Sorry, I probably missed something. Is this supposed to be an all loop result, or it's just
At the perturbative level, yes.
Oh yeah, okay.
So, but perturbative level is not everything. So let's squeeze in some non-perturbative effects as well. So at the perturbative level, we have this expansion here. And as it turns out, this expansion is actually does not converge, so it's asymptotic. And so we can also study non-perturbative effects. And the leading non-perturbative effect, we have this open string expansion over here. And the leading non-perturbative effects in these 2D setups, they're mediated by so-called ZC instantons. ZC instantons are some kind of Worldsheet conditions, also Worldsheet boundary conditions in which the open string can end, basically. ZC instanton means basically it's like Dirichlet type boundaries. So then we have a boundary, and then we put these boundary conditions there. And this has been studied in the last few years actually a lot by Ashok Sen and collaborators. And also this paper over here is like, it's an incredibly beautiful paper with lots of technical details. It's an amazing paper. And so just there was a lot of borrowing of their results. The leading order expansion takes this form where this thing over here is called the CC instanton tension. So TRS is called the instanton tension. So the CC instantons are basically labeled by two integers, R and S. This R and S, I don't know, I should have stressed it before, this R and S, they're related to the nodal singularities of the spectral curve. So, but then you can evaluate like this leading non-perturbative effects, and you can even match all of them to the matrix interval calculation. So the plus minus here, I think it's an interesting result. So I think this was very recent that people have uncovered that there is not just CC instantons, but there are also ghost instantons. The ghost instantons arise because the boundary condition is only fixed up to a sine. What this means in particular is that this contribution here, there's a plus and minus sign. So that means that there's either like if this object over here is real, then the ghost instantons are actually exponentially dominating over the CC instantons. Now, interestingly enough, for the complex lower string, this first contribution is purely imaginary. And so ghost and CC instantons are on equal footings. This object over here is called the annulus partition function or the cylinder partition function. This one is divergent, and for this you really need string field theory techniques, but this gentleman over here have done us a favor to tell us exactly how to calculate this. And these things over here in the JT language are called trumpet partition functions or punctured disks, and you can also evaluate those contributions. Yes.
Yeah, coming back to my question. So I think that this is the point where you're introducing actually the loop counting parameter or the. And then I think your proposal is then that you really typically sum this thing as a function of GS.
Yes.
That then the spectrum would actually cut off at that particular value for E, but indeed in a non-perturbative, somehow in a non-perturbative way, because obviously the metric model itself only has positive
density of states. Yes, of course.
So it has to happen.
No, it has to happen. I just don't understand how this that is related to the mu that I still don't.
Yeah, so I think your GS sort of labels the
okay.
the ratio of the mu and the linear data points.
Okay, that I have to think about. Okay, that's an interesting one. That I didn't know. Okay.
Isn't the mu just centering like a square root of mu in front of this?
I think it's just maybe because we said mu equal 2 always, and then it disappeared and I lost track of it.
Mu labels the location of the Liouville wall,
Yes.
and then there's a linear Dilaton. The value of the Dilaton at the location of the Liouville wall.
Yeah.
That's your GS. So GS labels mu.
Okay, that's interesting. I didn't notice. Okay, that I didn't notice. Let's look at that's an interesting fact like here. But in principle, we can also add boundaries. We can also add asymptotic boundaries. Maybe this formula is slashing too much. Interrupt me with questions if you have questions. I know I've been very ambitious with telling you all the details of this project. But what I want to say is that in principle, you can also add asymptotic boundaries. So psi means some conformal boundary conditions. It can be for the experts in the room, this can be FCCT, ZZ, this can be some boundary condition, some conformal boundary condition. Actually, Seiberg and Sheet told us that FCCT times CC form a sufficient basis where we can get all the boundary conditions, but it's just some boundary condition. But then we get actually like for whatever boundary condition you so like, the formula to add these asymptotic boundaries is going trumpet. So a trumpet is this thing over here, or this one functional disk. Yes.
Do the boundary conditions on the two Liouville's have to be correlated? Like
No.
you have to, okay, so you can do CC on one and FCT on the other.
Yes. I mean, FCCT times CC in principle is a complete basis. And so you can get FCCT out of like, you can like span, it's a basis to give you all the boundary conditions, but they don't need to be covered.
So earlier when you said ZZ, there's ZZ on both of them?
No, there's CC on both, yes. And the relation between what I told you so far. So let's basically go back again a step. So we've calculated the string amplitude, so AGN over here, using Worldsheet or matrix interval. We glue trumpets, then we get this partition function set GN over here. Remove the trumpets, we go back to the string amplitudes. If you do some Laplace transform, you can also go from this partition functions to the omega gns, which were the resolvents in the matrix interval. Choose your trumpets wisely, and go from the omega gns to the agns. So all of those things are interconnected, basically what I told you so far. Very good. Now, my last chapter is 2D gravity. So what I told you so far, like in the beginning at least, was Liouville theory as a two-dimensional CFT. I never had to make use of an action or anything. I just used that the semiclassicals and Donato have solved the theory for us. However, the Liouville theory also admits an action formalism, and this is maybe something that you have seen. So the Liouville theory as an action has this exponential term here, which really gives it the name Liouville theory, and then it's a kinetic term and a linear term here. And then the tilde subscript means that this is fiducial, it's background. So it basically means that in 2 dimensions, where my metric has 3 degrees of freedom, I can gauge 2 of them with the difference, and then what's fluctuating is phi, is this Liouville field. And again, the Q parameter is B inverse plus B. But then this is my Liouville action. So this is a Liouville action of one Liouville theory. And of course, for this Liouville theory to be the Liouville theory that I want, to be the Liouville theory set of charge 13 plus I lambda, this B parameter over here again gets this phase, pi over 4 phase. So we are in business, like if the B has this phase. But I still don't want to look at only one theory, I want to look at the combined theory. I want to look at S of phi plus S star of phi, because S star of phi is a complex conjugate Liouville theory. So I look at this combination. So this combination is from an action formalism, the complex Liouville spray. I do this transformation over here, and then I can bring this combination into this pretty cool looking formula. So phi here now is a scalar. R is the Ricci. It's really the Ricci. It's not the fiducial Ricci. It's a physical Ricci. So I have a phi times R term, and then I get this sine 2 pi phi here. And because of this sign, this is because we call this sine Dilaton gravity theory. JT gravity has a linear term there. So JT gravity is a Dilaton gravity theory with a linear potential, and the complex Liouville string has a sine Dilaton gravity theory, has a sine potential. Let me stress that this has also been studied by other authors. And we can study the equations of motion of this theory, and this is the equation of motion for the Dilaton phi, and this is the equation of motion for the metric. Now let's go ahead and solve that thing. Let's solve these equations of motion. And a way to solve these equations of motion is that you observe that this sine mu over here is a killing vector of these equations. And if you're going on a generic Riemann surface, so don't do the disk, go to a Riemann surface, a generic Riemann surface. A generic Riemann surface does not have any killing vectors. So if this is a killing vector of these equations of motion, it has to be 0 because there are no killing vectors on these Riemann surfaces. And for the only way for this to be 0 means that phi is a constant. So if this sine mu has to be 0, then phi needs to be a constant. And it doesn't need to be an arbitrary constant because it still needs to solve these equations. And so it needs to kill the sine. And for phi to kill the sine, phi needs to be an integer. It needs to be a constant and a constant integer. And this is again the m. So this is the m that we saw from a bootstrap approach that we saw in the matrix integral as the branch points of the spectral curve. And now it's the m of the Dilaton. It's the saddle of the Dilaton. And very interestingly, if you plug this phi star into this equations of motion, then you find that the Ricci is oscillatory. So you find that like the Ricci is either +2, -2, +2, -2, +2, or -2. So you basically find a Dilaton gravity theory which has both ADS2 and DS2 saddle. Okay, let me stress, the DS2 saddle comes with a -- signature. So you need to flip the sign of the metric. Yes.
If you take, for that statement, you took the worldsheet to be of higher genes, because if it was gene is 0,
Yes,
that would be for the.
exactly. And I'm never on the disk. G and N are always like higher. I mean, it's interesting to study the disk as well. And there, like Andreas is in the audience who has studied this theory on the disk. It's an interesting question. And other people as well have studied this on the disk of course.
The lecture started with a sphere Why are you skipping past the sphere? I mean, you actually started the lecture with the sphere. You've got perfectly good plus signature DS2 vacuum saddle on the sphere. DS2 literally is a sphere anyway.
Yes. There's no reason why I'm skipping this here. It's just a choice.
Both vector are there, both the ADS or not, the sphere just becomes DS2 only, or not?
Yeah, I just didn't include this here. No, actually, wait, no. Wait, I'm not confused.
They're both sides.
Yeah, no, I just skipped this sphere. What do you mean the no puncture sphere?
I'm just asking if the same two signs.
We're talking about the sphere without punctures, right?
Yeah.
Yeah, the sphere without punctures, I skipped. The sphere without punctures is divergent. This, okay. So that's I have this in my outlook only. I wanted to surprise this. It's an interesting point though. So the sphere without punctures diverges, which I think is an interesting point because it's a feature of Dilaton gravity theories. So DS2 JT gravity diverged on the sphere. ADS2 JT gravity diverges on the sphere. So sine Dilaton gravity theory on the sphere diverges. The Virasoro minimal string on the sphere diverges.
And even on the disk.
Yes, exactly. So the disk and the sphere are difficult. So the disk without punctures, the sphere without punctures are difficult. And I don't know what to make out of this. Like, what's the meaning of this divergence? This divergence. It's a very interesting point, though.
In some of the old work on matrix models and urban theory, there is some way of making sense of the sphere by taking.
Yes, because I think as long as you don't take like in the 2p minimal string, for example, I think if you calculate the sphere partition function, it's perfectly finite for finite p. Only when you take p to infinity, then that thing explodes. So it seems to be really a feature of this kind of like this double scaling Dilaton gravity theorist. It's an interesting question that I wonder whether it's a feature or a problem, like whether we can understand this or whether it's really something that tells us that we just have to discard these theories as theories of the sitter, for example. But say we managed to make peace with the divergent sphere partition function, then what we accomplished is that we found a Dilaton gravity theory, and yeah, I'm a native German speaker, so my D is capitalized, I'm sorry. So it's a Dilaton gravity theory with a de Sitter that's dual amplitudes. And just stressing, like Kotler and Jensen had this recent paper as well. So where they talked about de Sitter JT gravity and analytically continued the matrix integral. Let me just say that, like in this work, we know we're analytically continued the matrix integral. We derived the matrix integral from scratch that was dual to this Dilaton gravity theory for the Sitter Wi-Fi. Very good.
So in your case, the metric has plus signature.
For the Sitter satellite has minus signature.
It's also an analytic continuation of the ADSL. Okay.
Yeah, well, as you just said, it has minus signature if you're in genus G, bigger than 1.
Yes. But on the sphere,
On the sphere, it has plus signature.
but on the sphere, the thing diverges.
She's rejecting the solution on the sphere, but the theory has a classical solution on the sphere with plus signature.
I mean, if you study this theory on the sphere, so if you study this theory on the sphere, then you're just infinite.
Yeah.
It doesn't look infinite semiclassically.
I think what you see, if you I like looking at it from this S of phi plus S star of phi. So if you put this on the sphere, then you still need to divide by the Möbius transformations. And the Möbius transformations are 3 generators on the sphere. But this thing over here has 6 zero modes. So if you look at the one-loop contribution of this S of phi plus S star of phi, it has 6 zero modes. And so it's more zero modes than what you can gauge fixed by some Faddeer-Popper mechanism of PSL2C. And so that thing is 0 or infinite. It's just.
It's infinite.
It's infinite. Yes. But you can still running out of time, but you can also study the string amplitudes, of course, from a pathfinder perspective by understanding like this expression over here. And then in the I just put these drawings back here of the string amplitudes. So now what we have uncovered that previously, from a medium integral perspective, the m's were the branch points. Now this integers m's, this integers label the sitter and anti-de sitter vacua. So to some extent, what you can like think about this is like it's a universe transition. So you have a universe transition that's labeled, I don't know, for example, by some de sitter, and it goes to some ADS. So it goes from some de sitter to some de sitter. So like these m's now, because they label like different like universes, it's like universe transitions, like transition amplitudes between universes. I cannot tell you whether like one of the de sitter or anti-de sitter is more stable, but that's an interesting question. Right. Any questions? Okay, I don't know. Hopefully you'll tell me. I have one more chapter, but in principle, I can also just give it as an outlook and as an application.
I think it's fine. We have lots of questions.
Okay, so I won't take too much of your time, but I think this is an interesting application. I have to admit that like this is really an application. So we're borrowing a lot of Hermann's results. So, and slashing, what I mean here is that if you look at 3D de sitter, so okay, actually, let's stop for a second. Forget what I told you so far, just a second. Forget that we studied this 13 plus minus I lambda theory. And let's just like look at like PSL2C translation theory. And then we will see that like actually our complex global string makes a nice appearance here. So sorry, don't forget everything what I told you, but just like take a step back for a second. So we can use that 3D de sitter can be equivalently represented as some PSL2C translation theory. And what we can do then is that we can quantize this PSL2C translation theory. So take some Cauchy slice sigma Gn, and let's quantize this theory. Let's find the Hilbert space of this theory. And so if you go to Transimus formalism, in order to quantize this theory, what you need to solve is 6 first-order constraints. So just to maybe like the language that you have heard in this context are the Wheeler-DeWitt equations. So if you don't use Transimus formalism, but you use metric formalism, then this is the Hamiltonian and the momentum constraints. Hamiltonian constraint is known as the Wheeler-DeWitt equation. But if you want to make your life simpler, you go to the Transimus formalism, because in the Transimus formalism is a first order constraint. In the metric formalism is a second order constraints, and famously therefore they're difficult to solve. But in the Transimus formalism, these first order constraints are solvable, and actually like Hermann has done this for us in like 2 papers. And what we find is then that the Hilbert space of this Cauchy slice is spanned by conformal blocks. So a product of left and right moving conformal blocks, for example, charge 13 plus IR, and they have the punctures need to have conformal dimension 1/2 plus IR. So the punctures are looking like representing the principal series in PSL2s. So this is pretty cool because we basically uncovered again this 13 plus I lambda and exactly these values for the punctures that we've seen before in the string amplitudes. So because now, once you have the wave functions, the additional ingredient that you need to give the theory to really define a Hilbert space, you need to give it an inner product. And so take this wave function and give it an inner product. And this is a very natural inner product, I think. So you take the absolute value squared of this wave function and integrate over the moduli space of this Cauchy slice. But this expression over here already looks incredibly similar to something that we've seen before. So this expression looks, if you take the wave function to be this correlation function of the Liouville theory, which exactly had the right central charge because it was a correlation function and Liouville theory central charge 13 plus I lambda. And all the p's had conformal dimension 1/2 plus IR. So if you take the wave function to be this object over here and to take this wave function to be spanning this Hilbert space, then these norms of these correlation functions are nothing else than the string amplitudes. And now let's take this Cauchy slice to be spy plus. Let's take this Cauchy slice to be, let's bring this Cauchy slice in DS3 to be infinite future spy plus.
Is this inner product defined in this way equivalent to just do the path integral of the term times between the two Cauchy slices?
I don't think I have 2 Cauchy slices. I have only 1 Cauchy slice.
Yeah, but in
oh, sorry. I
yeah,
think I answered.
in a kind of path integral definition for inner product for gravity setting.
I don't know.
You know, we have two constants and integral between as an inner product. Is this equivalent to?
I don't know.
Okay.
I don't know. But now let's take this Cauchy slice to be still like take this Riemann surface, sorry, the surface sigma Gn to be the surface at square plus. And then the punctures they by this formula over here, by this relation between mass and conformal dimension, they extend the Wilson lines in the bulk of some non-dynamical scalar fields. And for like basically this to be in this form half plus IR, M needs to be much bigger than 1 over L de Sitter, so these need to be very heavy particles. So they don't correct. So, and now once we bring sigma Gn to be basically square plus, the interpretation of what we calculated before using matrix integrals or using bootstrap, or that what we cut out, our spring amplitudes are like the cosmological correlators of these massive non-dynamical particles. And the moduli space integral is like it's an integral of all the possible matrix on square plus. So what we gained is something that we might want to call a DS3 matrix integral correspondence. Let me stress that like this is different than DSCFT, because in DSCFT we map partition functions to wave functions. In principle, we don't have access to wave function, we have access to the norms of. So our resolvents in the matrix integral, they don't give us a wave function, but the resolvents in the matrix integral give us cosmological correlators. They give us the norm of the wave function. And very good. And okay, this is just an open question. I don't know.
But you didn't. But in this way, you cannot compute the inner product between two different states. Yeah, there is only have
Yes.
more. Oh,
Yes.
Okay.
I think so. Yes.
Okay.
I
So
mean,
this is not
it's-
really inner product; it's just the norm.
It's a norm.
Okay.
Yeah.
The worldsheet integral, before you do the integration, that you are calculating some amplitudes or maybe square of amplitudes
You mean-
for specific values of the moduli, right?
Yes.
Yes. Can you repeat your question? I think there were too many people in the audience that were saying yes before I was like.
I mean, if you wanted to calculate the amplitude you produce two particles at a given distance, it is giving you that.
You mean,
Integrate over the distance.
oh, you mean this?
Yeah.
Yes, I think so, yes. And this is just, I don't know if people have strong opinions or not on this equation here. This is just to say that like in the previous slide, I showed you that we're integrating over all the matrix on square plus. So it's more the question of whether like once we integrate over all the matrix, should we also sum of all the topologies? Should we include all of the topologies of square plus as well? So should we actually really look at this equation over here? And then of course, like there are non-perturbative effects here that we might want to start taking into consideration as well. But again, 2D, low D, we have complete control over all these non-perturbative effects, which is I think pretty cool. So this is my summary slide. I hope I was not too ambitious. I hope I didn't lose too many people. As a summary, let me say that we have these string amplitudes, which were the basic observables of the complex global spring, which we bootstrapped using this formula over here. Then we found the spectral curve of a 2 matrix integral that gives us the string amplitudes using some Feynman rules or using some Mirza-Kani type recursion relation. This summing over all the genera, this object over here is not convergent, it's asymptotic. And so there are non-perturbative effects that we need to take into consideration. You can also calculate the string amplitude using a Dilaton gravity path integral. And there's a nice interpretation of these string amplitudes as the cosmological correlators in DS for the unsquared plus. Just some some open questions. In most of, basically in all the discussion towards the end, I was living on square plus. I was basically considering only the global patch of the city. An interesting question might be, is there some relation to the static patch as well? In the end, the static patch is what we see. So, and is there some relation in the de Sitter entropy? So, I mean, as you might know, like both the global patch and the static patch bifurcated a sphere. So maybe these two patches actually are somehow related, and we can learn something about the static patch as well. I don't have much to say about this, unfortunately. So, but if you study this sine-Dilaton gravity theory and the disk, there seems to be some relation between the sine-Dilaton gravity theory and the double-scaled SYK model. But the arbitraries that have been calculated in this story are different than what we are calculating, because they're calculating boundary correlation functions on the disk, which is not something that we are calculating. So it's unclear what is the relation here. And in the end, like, we found a non-perturbative completion in terms of a matrix interval. So it seems a bit inconsistent. I just don't know like what's the relation to double scale SYK. Finally, let me stress that our wave function as this global correlator is different than what you might want to call a Hawking wave function, where you sum over handle bodies. So I don't know what's the relation to there. There has been a recent interesting paper by Victor Godet on this. It would be nice to understand like what's the relation. Again, this repetition function, is it a feature? Is it a problem? Like, should we discard models that have an infinite repetition function in the context of the sitter or not? Or is this a feature of the Dilaton theories? I don't know. Like, this question I find interesting, and although I have no answer. So the sitter JT gravity was a dimensional reduction of Schwarzschild de Sitter. Can we see our model as some dimensional reduction of some maybe 4D Rising-Nordstrom black hole, which famously, depending on how you zoom into extremality, has ADS2 times S2, DS2 times S2, and Minkowski. So is there some sort of dimensional reduction there? In the landscape, in this landscape picture that I drew before, the dual theories are always matrix integrals. One theory pops out there, so that I actually didn't draw. One theory that pops out is a so-called C-equal-to-1 string. A C-equal-to-1 string is a model where you couple a time-like-free boson to a Liouville CFT. Time-like-free boson means central charge symmetrical to 1. You couple it to a Liouville theory, central charge 25, so it has central charge 26 again. And then this C-equal-to-1 string is dual to a matrix quantum mechanics. So like you get emergent time somehow. So the question of how we find this emergent time, I think is very interesting, and we would like to understand like how this, why is this so special? Like what is so special about this thing over here?
Could you just simply analytically continue? What do I get?
I don't know. Also, like, I mean, I think it would be very interesting, you know, like a group in Harvard a few years back, including also Victor, they have like used a lot of machinery, like a lot of bootstrap machinery to get the kind of string amplitudes of this theory. It would be interesting to see whether there's some recursion relation for the C-equal-to-1 string as well. And I don't know, I think last but not least, like, of course, you can study all of this in supersymmetric version as well. And maybe if you add enough supersymmetry, this negativity of the density of states goes away or something, I don't know. But it would be interesting. Well, thank you so much.
In the gravity picture, the sitter vacuum, but you also have ADS2 vacuum, so what role did they was it related to this?
I mean, I think the question maybe is like, can we have DS2 without ADS2?
You have both.
Yeah, both, exactly.
And
Okay.
so what this answer is, from the
Exactly,
point of
yeah,
ADS2 vacuum, but what are they?
Both of them were equally stable. Both of them, there's no reason to discard one over the other. They have the same meaning. It's just that they are both there.
I'm sure actually.
Is there a bubble solution? Bubble location solution for transition between DS and ADS vacuum?
Like in higher,
M is
you mean just Coleman the Locha?
M is conserved now. If the number M, the thing that labels your minima.
Yeah. I know which one, but I don't know why it should be conserved. What do you mean by that?
At least it's conserved on each vertex. At least
Yes.
you're drawing it in the bulk of your
Yeah.
diagrams.
Yeah.
Not conserved throughout your whole.
No.
So then you can have.
You can have this transition amplitudes, yes, but I think normally, like if I remember correctly, then sometimes it's said that like one of the vacua is still more stable than the other one. But we cannot say anything like this. So a question whether like one of the vacua is more stable than the other one. This is a calculation that I cannot give you an answer to this question because I don't know.
So the idea is if you include the non-perturbative corrections, the eigenvalue distribution should stop at E naught.
The idea is that at the zero of the eigenvalue distribution, if you evaluate the action, a different saddle starts becoming the dominant one, and so you have to deform the contour. But how you deform the contour, it's a hard question for it to make sense.
If you don't want to worry about the non-perturbative contributions, can you sort of artificially restrict the eigenvalues to lie in a certain range in your ensemble?
I mean, for the perturbative effects, this zeros don't do anything. But I think if you artificially like I don't know, just restricted to be living in this interval, you're not doing anything good to yourself, because I think there's important physics to be learned from the fact
Would you lose the duality to the sine dilaton gravity?
Say again?
Would you lose the duality to sine dilaton gravity?
No, I don't think so.
This idea that you fix this problem with a negative eigenvalue distribution is a hope, or, I mean,
No, I think this is true. I think
I mean, you are assuming the model is well defined.
yes.
And it's not completely obvious from what you said that the model is well defined.
I mean, okay, and then let's put it this way, it is a hope. I mean, I think it is a hope that I think makes sense, that gains some hope, because the zero exactly occurs at the point where we need to start taking non-perturbative effects into consideration. So if the zero would have occurred somewhere, I would have been like, okay, yeah, we did something wrong, or something is not right. But because it's exactly at the point of non-perturbative effects, where in principle we know that something happens in the matrix integral, so the effective action that's felt by one of the eigenvalues, there's a different saddle that we need to start taking into consideration. And so the contour that we evaluated everything before needs to get rotated somewhere in the complex plane. So from that point of view, I think there is hope that like what we're doing is correct. We just don't know how to do it.
I mean, namely, if we see an eigenvalue distribution that goes to zero, we would say we just have this range, right, for a matrix. That's why wouldn't that be the right answer?
I think
For
when
a
you do,
semicircle distribution, I mean, just for a Gaussian matrix, we have a finite range of eigenvalues.
But there ends at a branch point. And
Yeah.
I think that space it doesn't, there's no branch point of that.
I think that, that literally just take the difference of the discontinuity of the resolvent, and if that is the well-defined spectral density, that should be positive. And they just say that that's a function become negative somewhere. That means it's a instability in a matrix integral non-perturbatively.
Does this problem occur in this Versora minimal string? I mean, the earlier mentioned that.
I mean, wait, sorry, yeah, so sorry, for the Versora minimal string it occurred as well, and it also like some sort of it occurred also in JT the sitter, where Douglas just left or no. So in ADS 2 JT.
So it's not
in the
new to
Versora.
this one.
In the Versora minimal string, there was one specific case where it did not happen. So in the Versora minimal string, which was the case where we coupled time-like to space-like Laurent theory, time-like being a Liouville CFT percent charge less than 1, space-like bigger than 25. If you zoom into 1 and 25, then it didn't happen.
Right.
So, and we don't know why it never happened there, but it's an interesting point that there it did not happen. But other than that, in all this kind of double-scaled Dilaton gravity theory dualities that I'm aware of, it happens.
I have a question related to the one I just asked. So you say the modular space integral is divergent at some pole or something?
Yes.
Right.
So you have the poles basically, and if you have this plane of all the poles, so this is the case where all the momenta are along the 45-degree line, and so like each pole carves out like kind of a triangle, and for this case, this white region is where the integral is always convergent. So you always find a region where it's absolutely convergent.
So the boundary are not branch cut; they are just literally isolated poles.
Yeah, but the poles they're carving out from triangles.
Oh, okay. And is the infinite sound formator also divergent at this point?
If you choose your bees to be of this form, yes, it's convergent here. But if you choose, it's a choice. Like in this 13 plus minus I lambda Liouville theory, and if this complex conjugate momenta along this 45-degree line, it's convergent. There, it's not. Like, sorry, this is just a comment again. So I was too lazy to draw all this. But so the point that I want to stress here is that the white region is the convergent region, but you see that at some point
Yeah, sorry,
it's closed.
so you have two formula, one is integral, the other is infinite sum, right?
Yeah.
The convergent region for convergent region for these two formula are the same?
Yes.
Okay, I see. And what's the physical meaning of this pose? This divergent pose, do they have a physical meaning? Location.
I don't know.
Okay,
Yes.
Yeah, for the negativity, I'm not sure if it's relevant or not, but what you call energy and what we call energy is slightly different. But the rho of EdE is the same expression. But we choose it, well, we have a different parameter than when you call ES energy, and then the density is positive everywhere. So I'm not sure what really makes one call something energy, but
Yeah. I mean, yeah. Yeah.
maybe
I mean,
it's
it's-
helpful, maybe not.
It's different. I think just, yeah, it's a different setup. So, yeah, it's interesting, like, but I hope we can solve the discrepancy.
All right, are there any last urgent questions for Beatrix? If not, in the interest of time, let's chat more in lunch.